Hello science fans, Bill Nye here, and today we're going to embark on an exciting journey through the world of matter. Today we're diving into the fascinating world of matter, the stuff that makes up everything around us. Matter is all around us, in every object we see and touch. From your chair to your phone, it's all matter, but not all matter is the same. Each object has unique properties that define its use and functionality. You can't build a skyscraper out of jelly, right? That's where mechanical properties come in. These properties determine how materials respond to forces and stresses. These properties tell us how materials behave under force, like a material's personality. Some materials are strong and rigid, while others are flexible and soft. Engineers and designers need to know if a material is strong, flexible, or brittle. This knowledge helps them choose the right materials for their projects. Understanding these properties helps us make better choices and appreciate the science behind everyday objects. It also allows us to innovate and create new products. From springs and mattresses to bicycle frames, mechanical properties ensure things work as they should. They provide the necessary support and flexibility. They determine if something bends or breaks, stretches or shatters. These reactions are crucial for safety and functionality. Imagine clay versus a rubber band. One stays squished, the other snaps back. This difference is due to their distinct mechanical properties. These are plasticity and elasticity, just two of the properties we'll explore today. Each property gives us insight into how materials can be used. We'll also look at strength, stiffness, and more. These characteristics help us understand the limits and capabilities of different materials. By the end, you'll see the science in a paperclip and the engineering in a car bumper. These everyday items are designed with specific properties in mind. This knowledge is fundamental to our modern world, keeping us safe and pushing creative boundaries. It allows us to build safer buildings, create innovative products, and improve our daily lives. So, get ready to explore the amazing world of matter. Let's go. Together, we'll uncover the secrets behind the materials that shape our world. Let's start with two fundamental properties that shape the way we use and understand materials: elasticity and plasticity. These concepts are at the heart of everything from toys to skyscrapers, and they help explain why some things bounce back while others stay bent or reshaped. Elasticity is a material's ability to return to its original shape after being stretched or compressed, like a rubber band snapping back after you pull it. This property is what gives certain objects their springiness and resilience. It's the bounce-back property you see in trampolines, which launch you into the air, and in guitar strings, which vibrate to create music but always return to their original position. Plasticity, on the other hand, is when a material changes shape under force and stays that way, like modeling clay that holds the impression of your fingers or the shape you mold it into. Think of a blacksmith shaping iron into a horseshoe. The metal is heated and hammered, and it keeps its new form, demonstrating plasticity in action. Elasticity is all about temporary deformation. The material snaps back. Plasticity is about permanent change. The material keeps its new shape even after the force is gone. Most materials aren't purely elastic or purely plastic. Instead, they have a mix of both properties, which is why you can bend a metal rod a little and it springs back, but bend it too far and it stays bent. For example, bend a plastic ruler gently and it will spring back to its original shape, showing elasticity at work. But if you bend it too far, it might stay bent or even break, showing that you've pushed it past its elastic limit and into the realm of plasticity. Engineers and designers need to know exactly how much force a material can take before it changes shape permanently. This knowledge is crucial for building safe bridges, sturdy buildings, and reliable products. Elasticity gives us flexibility and energy return, while plasticity allows us to mold, shape, and create lasting forms. Both are essential in our daily lives and in countless industries. These properties define how materials respond to forces every day, whether it's a car bumper absorbing an impact or a piece of clay being shaped into art. For example, you want a diving board to be elastic so it can flex and launch you upward, not plastic, which would leave it permanently bent after one jump. Sculptors and dentists, on the other hand, rely on plasticity to create permanent shapes, whether it's a statue or a dental mold that needs to hold its form. Elasticity and plasticity are two sides of the same coin, both crucial for design, engineering, and even art. Understanding them helps us choose the right material for every job. By mastering these properties, we can better understand, use, and even invent new materials that shape the world around us. Let's discuss strength and stiffness, two properties that sound similar but differ greatly. These characteristics are fundamental in material science and engineering, influencing how materials are chosen for various applications. Strength measures how much stress a material can handle before breaking. It's a critical factor in construction and manufacturing, ensuring that structures and products can withstand the forces they encounter. Think of a steel cable holding an elevator. It must be strong to withstand weight. Without sufficient strength, the cable would snap under the load, leading to catastrophic failure. Stiffness, however, is about resisting bending or stretching. It's the property that keeps a material from deforming under stress, maintaining its shape and functionality. A thick oak table is stiff, a thin plastic sheet is flexible. This difference in stiffness determines how each material can be used effectively in different scenarios. A material can be strong but not stiff, like spider silk, stronger than steel but stretchy. This unique combination makes spider silk fascinating for both scientists and engineers. Conversely, glass is stiff but not strong. It shatters easily. This brittleness limits its use in applications where impact resistance is crucial. Engineers choose materials based on the right combination of strength and stiffness. This selection process is vital for ensuring safety, durability, and performance in their projects. Airplane wings need both strength and a bit of flex. This balance allows them to withstand the forces of flight while maintaining structural integrity. Car suspension springs need strength but not too much stiffness. They must absorb shocks from the road while supporting the vehicle's weight. Strength is about survival under load. Stiffness is about holding shape. Both properties are essential for different reasons and applications. One tells you if it will break, the other how much it will bend. Understanding these properties helps in predicting material behavior under various conditions. Understanding these differences is crucial for designing everything from bridges to bicycles. Each application demands a specific balance of strength and stiffness to function effectively. It's all about finding the right balance for each application. The right material choice ensures safety, efficiency, and longevity in engineering and design. Let's explore brittleness and ductility, how materials fail under stress. Brittle materials break suddenly without much warning, like glass. They resist bending and shatter when their limit is reached. Ductility, however, is the ability to stretch into a wire without breaking, like taffy. Copper is highly ductile, perfect for electrical wiring. Ductile materials give warning before failure, stretching and thinning out. This difference is crucial for safety. Bridges made of brittle materials could collapse without warning. Ductile materials like steel bend and stretch, providing warning signs. Temperature affects brittleness and ductility. Some steels become brittle in the cold, a key consideration for engineers. Choosing between brittle and ductile materials depends on the application. Do you need it to hold shape until it breaks or give warning before failure? Understanding these properties helps us design safer, more reliable structures. Let's talk about malleability, a cousin to ductility. Malleability is the ability to be hammered or rolled into thin sheets without breaking. Gold is the most malleable metal, hammered into thin sheets for decoration. Aluminum is also malleable, used for foil and car panels. Malleability and ductility are often confused but differ. Lead is malleable but not ductile. It can be hammered but not drawn into wire. Malleability is crucial for manufacturing processes. It allows us to shape metals into complex, useful forms. From coins to car bodies, malleability lets us press and form metals. It's about working with materials, not against them. Understanding malleability helps us create beautiful, functional objects. It's a testament to our ability to manipulate materials to our advantage. Let's discuss creep and fatigue, subtle, time-dependent failures. Creep is slow deformation under constant stress, like a sagging bookshelf. It's a concern in high-temperature applications like jet engine blades. Fatigue is weakening from repeated loads, like bending a paperclip until it breaks. Each cycle creates tiny cracks that grow until failure. Fatigue is critical in anything with repeated cycles, like airplane wings and car axles. The de Havilland comet crashes taught us about fatigue, leading to safer designs. Understanding creep and fatigue helps us design durable, reliable structures. It's about anticipating how materials behave over time. Engineers must consider these factors to prevent catastrophic failures. Creep and fatigue remind us that materials have limits. By understanding these properties, we can build safer, longer-lasting systems. It's all about designing for the long haul. Is there a rule for how materials stretch? Yes, it's Hooke's law. Discovered by Robert Hooke, it states that force is proportional to stretch. Pull a spring a little, it stretches a little. Pull harder, it stretches more. This linear relationship applies to anything elastic, like springs and rubber bands. Hooke's law works within a material's elastic limit. Beyond that, materials deform permanently or break. The law is often written as F equals sign, Kx, where K is the spring constant. A high K means a stiff spring, a low K means a loose spring. Hooke's law helps us predict and understand elastic behavior. It's a powerful tool for designing systems that are predictable and reliable. From car suspensions to diving boards, Hooke's law is everywhere. It turns stretching into a calculable science. Remember Hooke's law next time you see something stretch and snap back. Hooke's law isn't just for physics class, it's everywhere. Weighing scales use it. The spring stretch shows weight. Car suspensions absorb road shocks using springs. Engineers choose spring stiffness for comfort or handling. Even diving boards act like springs, storing and releasing energy. Bridges, building frames, and bones all have elasticity. Hooke's law helps design systems that are safe and reliable. It turns stretching into a predictable science. From pens to bungee cords, Hooke's law is fundamental. It allows us to design systems that are predictable and safe. The next time you bounce on a mattress or strum a guitar, remember Hooke. You're witnessing his law in action. It's the elegant relationship between force and stretch in our world. We've explored the mechanical properties of matter: elasticity, plasticity, strength, stiffness, brittleness, ductility, malleability, creep, and fatigue. Understanding these properties is essential for building our world. It's not just for engineers, it affects you every day. Your phone case, car, and kitchen knife are all designed with these properties in mind. By understanding them, you become a more informed consumer. You see the science in everyday objects. It fosters curiosity and wonder about the world. Science is everywhere, and this is a perfect example. The world of materials is vast and evolving. Keep exploring and asking questions. The world is full of amazing stuff. Until next time, keep exploring and learning.